This class we are going to see the thermal properties, right? So thermal properties, you know, the conductivity of heat, or resistivity to heat, or thermal expansion due to heat, thermal contraction due to heat. These all terms will come as the thermal properties of a material. All right. So we'll start. Thermal property refers to the response to a material to the application of heat. So when there's heat, okay, when there is heat, and if there is any change occurring, right? So that is response will be termed as thermal property. So you provide heat. If there is any change occurred, or if it show any response, that is termed as thermal properties. As a solid absorbs energy in the form of heat, its temperature rises and its dimensions increase, right? So when a body absorb heat from the nature, right? When you provide heat to that body, you automatically know that the temperature rises. So definitely that's going to happen, and its dimensions increase. So if you are heating a steel bar, right? So initially the temperature will increase, right? And then it will undergo some expansion, right? If you have seen this railway tracks, okay, there would be gaps in between two tracks, not in between the parallel tracks. I'm talking at tracks, right? So why this expansion is just for that. So if you take like tracks, so if there are two tracks, if you have seen, there is a gap between the tracks while putting this one, right? So this particular gap is to allow this material for undergoing thermal expansion. Say for example, there's a thermal expansion at 20 degrees Celsius, and at 40 degrees Celsius is different, right? So in case of that temperature difference, this can expand little bit more, right? This can expand little bit more. But in case if we have a like completely straight bars, with the expansion, what will happen? It will tend to bend. That will impose thermal stress, right? So either that will bend outside, or that will bend inside, or that will bend up, right? Up or down, right? That's possible. Because if there is length is increasing, but there's no space for it, that will be resulted in the bending, and it will create thermal stress. So that we will study what is thermal stress in the forthcoming lectures, right? So the form of heat, its temperature rises, right? First the temperature will rise and dimensions increase, right? So with temperature, dimension increase, right? It's never going to decrease. If you increase the temperature, dimension is going to increase. It can be length, or it can be area, or it can be volume, that will increase. The energy may be transported to cooler regions of the specimen if temperature gradients exist, and ultimately the specimen may melt, right? Energy may be transported to cooler regions of the specimen if temperature gradient exists. So the word temperature gradient means, right? You know, in a normal graph, the gradient means the slope of the graph, right? The slope of the graph is known as the gradient, that is the m. So if your graph is of like y is equal to mx plus c, this m is known as the gradient, right? This gradient is the slope of this line with x-axis. In other words, we will say that as tan alpha also, right? This angle, okay? So what they're saying here is, if thermal, that's it. Yeah, if thermal gradient exists, and ultimately the specimen may melt. Say for example, you are giving heat at this end, okay? You are giving heat at this end for a particular material, and you are holding your hand this way, okay? Can you feel the heat at your hand or not? This is a, say for example, this is an iron bar or steel bar, some bar. So temperature gradient means one location should have high heat, right? Heat is high or temperature is high, and the other location has low temperature, which means heat gradient can occur, right? So heat will flow from higher location to lower location, right? This way heat will flow. right? So when you heat it here at this end, right, the atoms vibrate and transfer the heat this way, and you will feel the hotness in your hand, right? You can feel the hotness in your hand. So that's why it stated the energy may be transported to cooler regions, right? So if you are heating here, which means a cooler region is here, right? Cooler region of the specimen if temperature gradient exists. So if there is a heat difference or temperature difference between this point and this point, right? If there's a temperature difference, then thermal flow will be there from this point to this point. So that's how the heat energy is transferred. And ultimately the specimen may melt. So once it increased than the melting point, the specimen will melt, right? So the melting point is different for different materials. So if it is aluminium, that is around 680, I think. The same thing for iron, it's around 1147 or 1536, right? So different materials, they have different melting points, but once the melting point reached, the material will melt, right? They will melt. Heat capacity, thermal expansion, and thermal conductivity are properties that are often critical in the practical utilization of solids. So these are termed as the thermal properties: heat capacity, thermal expansion, and thermal conductivity. These are termed as the thermal properties. So mostly these are termed as the thermal properties. So let's see one by one. So what is heat capacity? What is thermal expansion? What is thermal conductivity? We'll see the headings one by one. So first one is the heat capacity, right? A solid material, when heated, experiences an increase in temperature, signifying that some energy has been absorbed, right? So there's a material, right? You are providing heat, all right? So this heat is absorbed by this material, and due to that, the temperature of this material rises, right? Solid material, when heated, experiences an increase in temperature, signifying that some energy has been absorbed, right? So you are providing some heat energy. Due to this material absorb that heat energy, the heat energy of the material is increasing. Heat capacity is a property that is indicative of a material's ability to absorb heat from the external surrounding. So heat capacity is a property that is indicative of material's ability to absorb heat, right? So material, how much heat it can absorb is indicated by the heat capacity from the external surrounding. So external surrounding means you are providing some heat. The heat is not generated by the material, but you are providing some heat. Heat represents the amount of energy required to produce a unit temperature rise, right? So unit temperature rise, for in calculations, we will say at unit mass, unit temperature rise, the energy needed is the heat capacity, right? In mathematical terms, the heat capacity C is expressed as follows: C is equal to dQ by dt. So the change in the provided energy dQ divided by the change in the temperature dt is known as the C, right? That is the heat capacity, where dQ is the energy required to produce a dt temperature change, right? So dQ, this is the heat energy, and dt, this is the temperature change, right? Ordinarily, heat capacity is specified per mole of material, right? So heat capacity is specified per mole, that is joule per mole Kelvin, right? So this is a usual notation: joules, that is energy, per mole Kelvin. This is temperature measured in Kelvin, energy measured in joule, and this is for 1 mole of substance. So the unit is joule per mole Kelvin. The specific heat, often demonstrated as log S. Okay, specific heat is sometimes used. This represents the heat capacity per unit mass. Okay, so here the unit mass thing is not there for heat capacity. When it is coming as specific heat capacity, right? When it is coming as specific heat capacity, we have that unit mass thing, right? Unit mass. All right. So there it will come as joule per kilogram per Kelvin. So here it's per mole, right? This is the amount of the substance. But when it comes to specific heat capacity, that is joule per kilogram Kelvin, right? That is joules per kilogram Kelvin. All right. So this is the difference between specific heat capacity and heat capacity. These are no same terms, right? These are different terms. So this is a like sample diagram of how this transforming of the heat is occurring. Normal lattice positions for atoms, right? So these orange, these are normally how these lattices are placed in a particular material. Then positions displaced because of vibrations, right? When you provide some energy, that gains some energy, right? If you provide some energy, each atom will gain some energy, right? So once it gain energy, what will happen? It won't stay at a place, right? That will start moving here and there. So exactly like you guys, okay? Say for example, you are there in your hostel rooms, okay? And if you are provided with some money and go to buy things, what you will do, since you have extra money, you will run out and buy the stuff, right? So which means if you have extra energy, you can't stay at that place. So the case is similar for atoms also. If we give some extra energy, they can't stay at a place. What they will do, they will start vibrating here and there, and while they are vibrating, they will transfer the energy from one atom to other atom, right? So that is a kind of chain reaction. So that will travel throughout the material. So here you see schematic representation of the generation of the lattice waves in a crystal by means of atomic vibrations. So actually these orange spots are the spots where the electrons should stay. Due to you provide some energy, see some of them are going there, some of them are moving this way, right? So this region is kind of less dense and this region is more dense, right? So they are kind of vibrating. So they won't stay at a place, they will vibrate all the atoms. There are two ways in which this property may be measured according to the environmental conditions accompanying the transfer of heat. Right? So this C, that is heat capacity, can be measured in two ways. One is the heat capacity while maintaining the specimen volume constant, right? That is named as CV, right? That is CV. So C is the heat capacity and V is the at specific volume. So this is heat capacity at specific volume, right? Heat capacity at specific volume, or volume is constant, right? Similar way, there is a CP also, right? CP, that is heat capacity while pressure is constant, right? Pressure is constant. The other one is constant external pressure, which is denoted as CP, right? This is our CP, right? This P is for constant pressure, right? So this P denotes constant pressure, heat capacity, and this one, first one, denotes constant volume, heat capacity, right? So what is this constant volume heat capacity means? You have a particular volume, right? Say this is V. You are putting some material inside and you are providing heat, okay? When you provide heat, what will happen? Vibrations increase, right? They will not stay at a place, they will run here and there and collide with others, and energy will be increased. So due to that, what will happen? Pressure will be increased, right? Pressure will be increased, okay? So while having the volume as constant, right? While having volume as constant, what is happening is pressure will be increasing, right? Pressure will be increasing. CP means you have a container, okay? You have a container, okay? This is a lid, okay? So here I have some molecules, all right? Molecules are there, and you are providing heat, okay? So this I told you, CP, all right? So here the pressure is constant, which means when you provide heat, these particles will start move here and there and collide with each other. So which means pressure is increasing, right? As like here, pressure is increasing. In order to manage that increase in pressure, what will happen is this lid will start moving up. So this is not a tight lid. This can move up and down. It's like you have a roller door here, right? When the pressure increases, this lid move up, right? So once you provide like energy, right? Efficient energy at a stage, say for example, that is ended up in this place. Okay. Say for example, that is ended up in this place, right? So due to all these collisions, what will happen is actually it was there at the beginning, right? After all these collisions finished, this is moving upward and ended up in here. So here you see initial volume was this much, but the final volume is this much, which means volume is increased, right? Volume is increased, but the pressure is constant. Why? This is allowed to move freely, right? So if there is excess pressure, this can move up. If the pressure is low, this can move down, right? So it can keep the pressure constant. All right. So this would be the setup of the constant pressure heat capacity, right? This is how a constant pressure heat capacity works, right? Okay. So when the volume is constant, pressure will increase. When the pressure is constant, volume will be increased, right? So this is a like vice versa formula. If you want to keep one constant, the other one anyhow should be increased, right? So if you keep the pressure constant, volume is increasing. If you keep the volume constant, then pressure is increasing, right? So this is one is constant pressure heat capacity, and the other one is constant volume speed capacity. Constant external pressure, which is denoted as Cp. Okay, so this is the other one. The magnitude of Cp, right? Magnitude of Cp. What is that Cp? Constant pressure heat capacity is almost always greater than that Cv, right? Cv is constant volume heat capacity, right? So this Cp is almost greater than Cv, right? Almost a little bit. However, this difference is very slight, right? Very slight for most solid materials as at room temperature and below, right? So most of the solid material, why this is slight, I mean this difference is very low is solid material, the increase in volume would be little bit, not little bit actually, when compared to gas and liquid substance, the volume change of solid material is very low, right? So again, you can imagine, right? When you take a balloon and input the gas, right? Volume is increasing like this fast, right? Similar way, when you take some milk and cook it in the fire, what will happen? Initially, milk will like this. Then at some stage, it will come like this, right? So for gas state, that is balloon, right? Example, and liquid state, that is this milk. The volume change is kind of significant, right? But in the case of solids, the volume change is very low, right? Why? The thermal expansion of coefficient that we will study in the later stages, right? That is like in the power of 10 to the power -6, -5, something like that. So the change in the volume or length or area would be very less for solids, particularly for solids. So this is why for most solid materials at room temperatures and below, the difference is slight, right? Cp is greater than Cv, that's true, right? But the difference between Cp and Cv is very, very low, okay? Temperature dependence of the heat capacity, right? Temperature dependence of the heat capacity. Variation with temperature of the vibrational contribution to the heat capacity is a constant at constant volumes for many relatively simple crystalline solids is shown in the figure. So there's a figure, okay, below, right? Cv is 0 at 0 Kelvin, but it rises rapidly with temperature. So here, Cv is specific heat capacity at constant volume. So at 0 Kelvin, right? At 0 Kelvin, this is again 0. So if you start draw a graph, if you take this as CV and this as this as temperature x-axis and this as CV, starting point would be here. That's fine, right? But it rises rapidly with temperature. This corresponds to an increased ability of the lattice waves to enhance their average energy with ascending temperature. So this is the equation. At low temperature, the relationship between CV and the absolute temperature of T is AT cube, right? What will happen is this will rise like this fast. Why? That is ATU cube. So at 0 temperature, right? Temperature is 0, CV is also 0. That's fine. Why? If you put T 0, C is also 0. Okay. What will happen if you put T1? 1 cube is 1. You keep the T, that's a constant, no? So we'll keep it. And CV is also 1. When you put 2 for T, C would be 2 cube, that is 8. If you put 3 for T, CV would be 3 cube, that is 27, right? So your values will be 0, 1, 8, 27, something like that. So 0, 1, 8, 27, then 64, right? 125. This will be going like this. So this is the way the temperature relationship between CV and the absolute temperature, right? Where A is a temperature independent constant, right? So this A is a constant which does not have anything to do with the this temperature or with the gradient, right? This does not have anything to do with that. So CV, it's dependent of the heat, dependence of heat capacity at constant volume on temperature at low temperature 0 Kelvin. So it will start at 0, 1 and will end up in like 8, 27, 64. So just imagine if you increase the heat from 0 to 10, the temperature difference is just 10 Kelvin. Okay. If you increase it from 0 to 10, temperature difference will be just 10 Kelvin to heat capacity. That will be like cube of that. That is 10 into 10 into 10. That is 1000 into a is a general number, right? So that's 1000. So the heat change is very huge, right? So this is a rough explanation. What is actually happening? Energy absorptive mechanisms are also exist that can add to the total heat capacity of a solid. Okay, so what are the mechanisms that will actually contributing to this phenomena? In most instances, however, these are minor relative to the magnitude of the vibrational contribution, right? So the contribution could be minor, but there's an electronic contribution in that electrons absorb the energy by increasing their kinetic energy. So as I told you, if you provide extra energy, they will get it and increase their kinetic energy. When the kinetic energy increases, they won't stay at a place, they will start moving here and there. However, this is possible only for free electrons, those that have been excited from filled state to empty states above the Fermi energy level, right? So here are 4 terms, right? 4 terms. One is our CP, other one is CV, then K, then L, right? So first one is the CP, okay? So this is heat capacity at constant pressure. So usually we go for CP, right? That is joule per kilogram per Kelvin, right? Joule per kilogram per Kelvin. And here we have alpha. Alpha, I told you, thermal expansion coefficient, right? Thermal expansion coefficient, which means whenever you provide extra heat, right? Not extra heat. Whenever you provide heat energy, I told you there will be some increase in the length or area or volume, right? So that is this alpha, that is thermal expansion coefficient. That's you see in the range of 10 to the power minus 6. So this is why the change in the volume or length or area is very, very small in solids compared to the liquids and gases, right? And then we have K, that is conductivity, that is watt per meter Kelvin, right? Watt per meter Kelvin. So aluminium heat capacity is 900, then copper 386, gold 128, iron 448, right? There are a few alloys also. Brass, that is 70 copper, 30 zinc 375. Covar is there 55 feet, 29 nickel 460, right? These all are heat capacities. Then I have alpha, that is thermal expansion coefficient, right? So there, if you see, aluminum has the highest thermal expansion coefficient, and silver, that is 19, right? Also, we have brass, that is around 20, right? So these are the metals that can have a kind of at least little bit higher thermal expansions. All right. When you compare these metals with these ceramics and polymers, right? This area with this and this, ceramics you see here, the heat capacity almost they are in the same range, right? 700, 900, 700, 700, 800, 800, right? So silica, spinel, magnesia, alumina, soda, lime, right? Borosilicate, while their thermal expansion coefficient is very low. Very low in the sense compared to these metals, that is low. So alumina is 7.6, magnesia 13 point, right? And 7.0.9 point. All right. So a general term is the heat capacities of metals, right? And ceramics can be a kind of comparable, while in the case of alpha, that is thermal expansion coefficient, these terms, right? These terms, that is not terms, values. Thermal expansion coefficient of metal is a little bit higher than the ceramics, right? And further, if we compare it with polymers, right? Polymers have CP high, right? And they have the thermal expansion coefficient also high, right? Very high. So from this chart, what you can understand is you need to provide like less energy for these metals to increase the temperature, specifically for gold, silver, tungsten, right? Brass, right? So you need to provide less heat to increase the temperatures. If you compare these three, right? Metals and ceramics and polymers, polymers are the materials which need high amount of heat energy to change their temperature from one value to other. They need see 800, 1850, 1920, like that, right? So polymers are the materials which need high amount of energy to change the temperature by a unit value, while metals, and in metals particularly gold, silver, tungsten, these metals need less energy to change their temperature from particular degree Celsius to particular degree Celsius. That's a kind of unit, right? Right. Then we come to this thermal expansion. All right. The thermal expansion, I told you, the change in the length due to some temperature, right? So most solids materials expand upon heating and contract when cooled, right? So when you increase the temperature, length will also increase. When you decrease the temperature, length will also decrease, right? Common phenomena. And contract when cooled, right? So the word contract means reducing, okay? The change in length with temperature for solid material may be expressed as follows. So this is the formula to calculate the change of the length of a material with the change in the temperature, right? So LF minus L naught over LO equal to alpha into TF minus TO, right? So this LF is the final length, right? Final length means you heat it, and after heating it, that will reach some temperature now. So say for example, at T1 degree Celsius, this is L1, okay? At T2 degree Celsius, this is L2. Okay. So due to the change in the temperature T2 minus T1, due to you provide like some extra heat, this much increase has happened. Okay. So when you put these terms into this equation, LF is the final length. So that is L2, right? L2 minus LO is the initial, right? Initial length. So initial length is L1, right? L2 minus L1 upon LO, that is the initial length, L1 equal alpha. Alpha, I told you, it's given in the table, that is different for different materials. So thermal expansion coefficient. So that alpha into TF, that is change in the, not change, that's the final temperature. F means final, right? So final temperature here is T2 minus TO. TO means initial temperature. Initial temperature here is T1, right? So L2 minus L1 is equal to L2 minus L1 upon L1 is equal to alpha into T2 minus T1. So if you want to write this formula into these terms, right? So this term I just drawn to indicate you how is it actually happening, is equal to like this. So in other words, we can say delta L upon L naught, right? So this is the delta Ly change in the length, L2 minus L1. So that is only this much. So this can be written in other format also. So when you see LF minus L naught, that is L2 minus L1. So this is L2, this is L1, L2 minus L1 is this length only, right? That is actually the increased length. So I can put it as delta L. Why? This is the increased length divided by L naught, right? L naught is the initial length. So that's why this L naught is will be equal to alpha into, right? Alpha is the thermal expansion coefficient into TF minus TO. So TF is the final temperature, TO is the initial temperature. So final temperature minus initial temperature is the change in the temperature, right? That is delta T, right? So this equation and these equations are similar equations, right? So this way, or this way, or this way, these all are same. Delta L upon L is equal to alpha into delta T. You can say like that. Or else final length minus initial length upon initial length will be equal to alpha into final temperature minus initial temperature, right? These two are same formulas, right? This and this. Only thing is they are written in different format, where L0 and LF represent respectively initial and final lengths, right? So L0 I told you initial length and LF is the final length with the temperature change from TO to TF. Again, T0 is initial temperature and TF is final temperature. The parameter alpha L is called the linear coefficient of thermal expansion, right? So alpha I told you that is linear coefficient of thermal expansion. So there's an L is there, right? So this L is for linear coefficient. If it is V, that would be volumetric coefficient, right? If it is A, that is area coefficient, right? So when you see alpha L, that is linear coefficient, okay, linear coefficient. So that will indicate the change in the length, initial length and final length, okay. And if you have alpha A, that is area, right, area coefficient. So that will give you an idea of the initial area, and when you heat it, the final area, okay. And then we have alpha V also, right? So that is actually volumetric coefficient. So that will show you, you know, a change in the volume. So if this is the initial volume, the final volume, okay, these figures are not that good, but you can just imagine, no? So volume itself increasing means this way length should increase, this way width should increase, and this way height should also increase. It's a material property that is indicative of the extent to which a material expands upon heating and has units of reciprocal temperature C minus 1, right? Delta, sorry, not delta C, degree Celsius minus 1 is the unit of alpha. So how much extent a material can expand when you provide some heat, okay? So this will be different from material to material. Say for example, you are providing 10-degree increase in heat for both aluminium, copper, and iron, okay. So aluminium has a higher thermal expansion coefficient, so that will expand very much. Copper must have next to that, that will expand this much. But iron very low, so that may expand this much. But for all three materials, you have provided 10 degrees Celsius, right? Equal amount of heat. You provided an equal amount of heat, but they show different lengths. So this is the property of that material, which is denoted by the alpha thermal expansion coefficient or linear coefficient of thermal expansion. Of course, heating or cooling affects all the dimensions of a body with a resultant change in volume. Volume changes with temperature may be computed from delta V upon V naught is equal to alpha V into delta T. So in the similar way as like linear, so that was delta L upon L naught is equal to alpha L into delta T, that is linear expansion coefficient, linear change in the length. Here when it comes to volume, you have to just replace this all L with V. So delta V upon V naught will be equal to alpha into V into delta T. If it is like area coefficient, then delta A upon A naught will be equal to alpha A into delta T. That A would be indicating the area, right? So you can compute the value of either delta L or delta A or delta V by putting in this formula, right? Where delta V and V naught are the volume change and the original volume. So delta V is the volume change, V naught is the original volume, right? Respectively, and alpha V symbolizes the volume coefficient of thermal expansions, right? So alpha V shows the volume coefficient of thermal expansion. What you see here is alpha L, that is linear coefficient of thermal expansion, right? In many materials, the value of alpha V is anisotropic, that is, it depends on the crystallographic direction along which is measured. For materials in which the thermal expansion is isotropic, alpha V is approximately 3 alpha L, right? So for materials, thermal expansion is isotropic, right? So when there's a continuous or uniform change, this alpha V would be almost equal to 3 into alpha L. Okay, alpha V will be almost equal to 3 into alpha L. So this and this are alpha. This is a direct proportional sign. In a similar way, alpha A is directly proportional to almost, I can write even equal, right? Not always, to alpha L. Let's see how is that. Say for example, you have a length here, okay, and you heat it and you now got a new length, this one, okay. If you have an area, right, so when you heat this area, okay, when you heat it, what will happen? Along this length also length will increase. Along this length also length will increase. So this will come like this, and this will go like this. So here you see this way an alpha L is occurring. This way an alpha L is occurring, right? So here we have 2 alpha L, right? So that's why alpha A can be stated as 2 into alpha L, right? Only thing is it should be in isotropic condition. Isotropic means a kind of a uniformity in increasing, right? Similar way I can explain for volume change also, right? Volume means along with this area, I will have a thickness, right? I will have a thickness. Say for example, this is my initial material, right? So when you heat this, what will happen? Length will increase like this, okay. So at the end, I will ended up in having a material like this. So here I have already an alpha 1, sorry, not alpha 1, alpha L, that is linear coefficient of thermal expansion. This way another alpha L, and this way down the z-axis also I have an alpha L, right? So if I say this is x-axis and this is y-axis and this is z-axis, so x-axis I have alpha L, y-axis alpha I have alpha L, and z-axis also I have alpha L, which means now I have 1, 2 and 3 alpha L, right? So that's why this alpha V can be written as 3 alpha L, right? So that's why it's stated that for materials in which the thermal expansion is isotropic, alpha V is approximately 3 into alpha L, right? Approximately. right? It's approximately not exactly equal, but approximately. Atomic perspective, thermal expansion is reflected by increase in the average distance between the atoms, right? So I told you, when you provide energy, they won't stand at a place. They will keep on running here and there and everywhere, right? So due to this, the distance would be increased, right? Distance between the atoms would be increased. So this is how the thermal expansion is happening in the um, perspective of the atomic. So say for example, in this volume, initial volume, I had 4 atoms, right? Now they are in this distance. Okay, this is the distance. When you heat, what will happen? They gain energy, but they want to move here and there. So they will agitate or vibrate. So at that time, they anyhow will move. So this electron may move here, right? This electron may move somewhere like this. This can move like this. Okay, this can move like this. Why? Because they got the energy, so they can move. So when they are moving, that's a material. So if the electrons are moving, mean they are making high space, right? So due to that, the area is increasing, right? Due to that, the area is increasing. So this is the same phenomenon as like here, but here the perspective, I mean, what I am talking is about the movement of the atoms, right? Here what I am talking is about the, I mean, mathematical way, right? So thing is similar, but the way I am explaining is different. As noted in the table, linear coefficients of thermal expansion for some of the common metals range between 5 to the 5 into 10 to the power minus 6 and 25 into 10 to the power minus 6. So if you see the table, so all the metals, the range was like this. These values are intermediate in magnitude between those for ceramic and polymers, right? So if you check them, these values, these are lying between this value and this value. So these are lowest, these are next, and these are the largest, right? So here you see the values are ranging from maximum 25, 23 to minimum around 5.1, 1.6, right? So that's what he is talking about. These values are intermediate in magnitude between those for ceramic and polymer materials. As the following materials of importance box explains, several low expansion and controlled expansion metal alloys have been developed, which are used in applications require dimensional stability with the temperature variations, right? So yeah, here we have a table, right? Materials of importance. In one and other low expansion alloys, we will study that one. So why actually the table is important is because usually when we heat, you know, material will expand. So if the material is expanding, which means the dimension is high, right? So for materials which needs thermal stability, right? Thermal stability, we develop some materials, right? We develop mean kind of alloys are made, right? So say for example, usually the which one we'll assume piston, right? So we'll assume piston, right? And piston ring. So you know, piston ring has to move back and forth inside the piston, right? So you just assume this is piston and piston rings, even though my drawing is not that good. Okay, so this should move up and down, right? So this region we will have a seal, and this region also we will have a seal. Okay, and fuel will be supplied by one way and go out by the other way. Now my question is, when the fuel is applied and when there's pressure generated and fire occurred and then fuel will be exhausted. You might have studied this one in the automobile foundation automobile subject. So that's a phenomenon of ignition. When this thing happened, the engine usually actually piston and piston ring at room temperature, say for example around 30, will be rising to around some thousands of temperature. I'll put like 1000. Okay, 500, fine. Okay, so initially that is at room temperature, that is 30 degrees Celsius. Now it has increased to 500 degrees Celsius, which means according to what we have studied so far, there should be a thermal expansion, right? There should be a thermal expansion. But if there's thermal expansion at high temperatures, this gap would be fine for the metal to move. But at low temperature, this gap will be very large, which we don't want, right? So there are certain incidents where we need the thermal expansion to be controlled. We cannot leave it as it is. All right. So for those particular moments and applications, there are some alloys developed. Right? So that's what this sentence is mentioned about. Materials of importance also explain several low expansion and controlled expansion metal alloys. So here the expansion is deliberately controlled, which are used in applications require dimensional stability with temperature variations, right? So with the temperature varying, what's actually happening to the dimensional stability? So dimensional stability, I told you, not changing like frequently for the change in the temperature, right? So let's see that in 1896, Charles, this guy of France, made an interesting and important discovery that earned him the 1920 Nobel Prize in Physics. Okay, he earned it. An iron nickel alloy that has a very low, near zero coefficient of thermal expansion between room temperature and approximately 230 degrees Celsius. Right. So this alloy, iron nickel alloy, right? Iron is Fe, nickel is Ni. That has a very low coefficient of thermal expansion, so nearly zero. So does not have any thermal expansion between this range, room temperature and 230 degrees Celsius. So room temperature may be 30 degrees Celsius and this temperature would be 230 degrees Celsius. This material became the forerunner of a family of low expansion, also sometimes called as controlled expansion metal alloys, right? So he made it as a low expansion alloy. So this would be the first foundation for that. Its composition is 64% Fe and 36 weight nickel. So in that composition, 64% by weight is iron and 36% by weight is nickel. And it has been given the trade name of invar because the length of a specimen of this material is virtually invariable with changes in temperature, right? So up to this, I mean, in this temperature range, 30 to 230, the change in the temperature is like a kind of negligible. So in other words, we can say that is invariable. There is no variation in the temperature. So that's why the name invar is given. So first 5 letters INVAR, right? So that's why this name metal is called as invar, not metal, sorry, alloy, right? So alloy of 64% weight Fe and 36% weight Ni is called as invar because the variation of temperature is low, sometimes invariable, right? That's why the name is given. Its coefficient of thermal expansion near room temperature is 1.6 into 10 to the power minus 6 degrees Celsius minus 1, right? So when compared to aluminium, which is around 23, and gold around 13, silver around 17, this is very much less, around 10 to 12, 10 to 15 folds lesser than that of the thermal expansion of those metals, right? So this is a specialty with this invar, that is 64% Fe and 36% Ni. Heat treating and processing of invar will also affect its thermal expansion characteristics. The lowest alpha IL values result for specimens quenched from elevated temperatures that are then cold work. Annealing leads to an increase in alpha IL. So if they want to change that property, they will go for some heat treatment process. Other low expansion alloys have been developed. So there are some others also. One of these is called super invar, right? Because invar it has a thermal expansion of 1.6, right? 1.6 into 10 to the power minus 6. Then they have developed even better material than that, that is showing 0.72 into 10 to the power minus 6, super invar. So this is lower than the value of for invar, so almost half. However, the temperature range over which its low expansion characteristics persist is relatively narrow, right? So here the range of temperature is little bit less. Here you see from room temperature to 230 degrees Celsius, that is around for 200 degrees Celsius, right? Room temperature 30 to 230 degrees Celsius, so which is around 200 degrees Celsius, thermal expansion coefficient is 1 by 6 into 10 to the power minus 6. But for superinvar, yeah, that is 0.72 into 10 to the power minus 6. That is fine. But the temperature range is the problem. So it shows only at a particular temperature range. Right? The temperature range is so narrow, relatively narrow. Compositionally, for superinvar, some of the nickel in invar is replaced by another ferromagnetic metal, cobalt. So superinvar now has 63% Fe for 32 Ni and 5% cobalt, right? So this is actually the composition of superinvar. This has a low thermal expansion coefficient, but the range for that will occur is low, right? A kind of narrow. So here we have another alloy with the trade name of Povar, right? This is Povar, has been designed to have expansion characteristic close to that of borosilicate, right? Borosilicate is refractory material, as you already studied. For Pyrex glass, when joined to Pyrex and subjected to temperature variations, thermal stress and possible fracture at junction are avoided. So this is another alloy. Right? So here 54 of Fe, 29 nickel and 17 cobalt. So the components are same, 54 Fe, 29 nickel and 17 CO. Here 63 Fe, 39, 32 nickel and 5 CO. Right? So materials are same, but the composition is different. So these low expansion alloys are employed in applications that require dimensional stability with temperature fluctuations, including the following. So they need to stay steadily when the temperature fluctuates. So that's the purpose. So when the temperature increases, dimension will also increase. When the temperature decreases, dimension will also decrease. That's a general formula. But these materials are particularly made, which one? This invar, superinvar, povar. These are particularly made for tolerating the fluctuating temperature. So which means dimensionally stable when the temperature is fluctuating. Compensating pendulums and balance wheels for mechanical clocks and watches, right? So pendulum, when the temperature increases, what will happen? The length of the pendulum wheel will increase. So if the length increases, so when the temperature increases, the length will also increase, right? So when the length increases, the swaying time will also increase, right? Swaying time will also increase. When this swaying time increases, this will not show a correct time, right? This may lag in milliseconds, microseconds, and they will collaborate as a kind of seconds and then minutes, right? That's the problem with the pendulums and balance wheels for mechanical clocks and watches, right? So these watches and mechanical clocks, they have like small inside the wheels or gear setup, something like that, right? So you might have seen in this wall clocks, if you open it, you will find something with the plastic. That's fine. In case if it is metal, then they will, expand with thermal value. I mean, increase in temperature, and they will make problem with the times. Then I have structural components in optical and laser measuring systems that require dimensional stability on the order of wavelength of light, right? So these are few materials. Bimetallic strips that are used to actuate micro switches in water heating systems. So bimetallic strip, that is the structure of two metals, right? So these are usually used in iron box. One can be aluminium, and say for example other is Fe. So if the thermal coefficient of aluminium is high, right, this will expand fast. So when you increase the temperature, aluminium would have been here, right, and maybe this iron can go only up to here, right? So what will happen? This is tied, so definitely this has to bend like this. No, not that way. This will bend this way, right? That will bend. Okay, because this and this is tied now. This can't exhibit like this. so they will bend, right? So that's the example of bimetallic strips. Then I have shadow masks on cathodic ray tubes that are used for television and display screens. Vessels and piping for the storage and piping of liquefied natural gases, right? So these are some phenomena why this temperature fluctuations is not advisable in some particular applications, right? So this is why we need this low expansion alloys. So invar, super invar, and hovar. So these alloys have very low thermal expansion coefficient. So they are preferred for particularly some applications, right? Okay, ceramics. Relatively strong interatomic bonding forces are found in many ceramic materials as reflected in comparatively low coefficients of thermal expansion. So here the interatomic bonding is strong, low coefficient of thermal expansion, right? Typically range between 0.5 to 15. So their expansion is not very low, little bit low compared to metals. So pure silica is having a thermal expansion coefficient of 0.4 into 10 to the power minus 6. So ceramic materials that are subjected to temperature changes must have coefficient of thermal expansion that are relatively low and isotropic. Then we have polymers, right? Polymeric materials experience very large thermal expansion upon heating. So in the table, if you see, when you come, that's the table. When you compare, these have very large thermal expansion coefficient than other two. Experience very large thermal expansion coefficient upon heating and indicated in the range of around 50 to 400, right? While this is the case of metal around 5 to 20, now it's like 10 folds, 50 to 400. The highest alpha values are found in linear and branched polymers because of the secondary intermolecular bonds are weak, right? So when we are talking about these polymers, I told you, if the structure is to be strengthened, then interconnection chains must be there and aromatic links should be there, right? With increased cross-linking, the magnitude of expansion of coefficient diminishes. Why? There are too many bonds. Say for example, you have only this one. This is a polymer. Okay. You have another polymer also, right? Assume that it is bonded like this and like this, right? So this polymer will have less tendency to expand. Why? There are too many too many branches or links, cross links are there, which need to be expanded. But here, it's not the case. If you provide heat, all the heat will be supplied to these single bonds and that will expand, right? So that's why it's mentioned. High alpha L values are found in the linear, right? Linear and branch polymers, right? Linear and branch polymers. With increase of cross-linking, right? With increase of cross-linking, the magnitude of the expansion coefficient diminishes, right? Diminishes means reduce. So when the this chains bonds, when they increase, the thermal expansion will decrease, right? Lowest coefficients are found in the thermostatic network polymers such as phenolic formaldehyde, in which the bonding is almost entirely covalent. So phenolic formaldehyde, there's a phenol, right? So which means aromatic chain is there, right? So here the thermal expansion value is so less, he's saying. Thermal conduction is a phenomenon by which heat is transported from high to low temperature regions of a substance. Heat will be flowing from the high temperature value to low temperature value, right? Not value, region, right? Heat is transported from high to low temperature region. So here would be the high temperature region and here would be the low temperature region. The property that characterizes the ability of a material to transfer heat is the thermal conductivity. So thermal conductivity is the characteristic of a material to transfer the heat from one location to the other, right? It is best defined in terms of this expression, right? Q is equal to minus K dt by dx, right? Where Q denotes the heat flux. This small q, this denotes the heat flux. In the previous equation, we put capital Q. Capital Q is the supplied energy, right? Small q is the heat flux or heat flow per unit time per unit area, right? So say for example, I have something like this, okay, a kind of rectangle, okay, and the heat is traveling by this way, all right. So the heat is actually traveling in this cross section area, right? Heat is traveling in this cross section area. So when you cut, right, again you need to take that particular area, okay. We need to calculate only on this. That's why it's mentioned heat flow per unit time per unit area, right? So time we can measure, right? From here to here it will take t minutes, okay, and per unit area. So this area means we can't increase the area and measure that. That area should be considered. I mean constant. All right. Area being taken as the perpendicular to the flow direction. So if it is heat is flowing this way, perpendicular to that direction, so that is through this area. So whatever the area the heat is passing through, you need to take that particular area. You can't take this area or this area. Whatever the area heat is passing through, you have to take that particular area. K is the thermal conductivity and dt by dx is the temperature gradient through the conducting medium, right? Dt by dx is the temperature gradient through the conducting medium. So dt is the change in the temperature, dx is the change in the distance. So dt by dx will give you the temperature gradient, right? So in this much distance, how much is the change in the temperature? So say for example, here I have T2 and here I have T1, right? And this length is x, right? So this equation will be coming as minus k into dt2 minus dt1 divided by x, that's the distance, right? Changing the distance, that will give you the q, right? Heat flux. K is the thermal conductivity, so which is given the table, and dt by dx is the temperature gradient through the conducting medium. So here this K is the thermal conductivity, that's fine. But why do we have this minus here is due to the graph. So usually heat will flux from high temperature region to the low temperature region, right? Always heat will flow like that. So this is why we keep a minus, because the gradient of this graph is minus, right? The gradient of this graph is minus. That's why we have minus K over there. The units of Q and K are watt per meter square. Q is the heat flux, that is watt per meter square, and K, that is conductivity, is watt per meter Kelvin, right? So these are the units respectively. This equation is valid only for steady state heat flux. So this equation is valid for steady state heat flux, which means the heat is generally flowing from here to here, right? For situations in which the heat flux does not change with time, right? So steady means that's a thing. So there won't be any change with the time. Also, the minus sign is the expression indicates the direction of the heat flow is from hot to cold, right? So high temperature region to low temperature region. That's why this minus sign is there. So this is the equation for thermal conductivity. Q is equal to minus K dt by dx, right? Q is the thermal flux, sorry, heat flux. P is the K is the thermal conductivity value. dt is the change in the temperature, and dx is the change in the distance, right? Thermal stress are stress induced in a body as a result of changes in the temperature, right? So when there is change in the temperature, there are so many possibilities. The length may increase, right? Vibration would be there in the atoms, right? So due to these various acts, there would be some stress. An understanding of the origin and nature of thermal stress is important because these stresses can lead to fracture of undesirable plastic deformation, right? So as like usual stress, these are thermal stress. When you change the temperature, this stress will occur, right? For the summary, so here the equations are given. So this is for heat capacity, C is equal to dq by dt. Here is the thermal expansion equation, right? Linear coefficient. Okay, linear coefficient of thermal expansion. Then this is for volume expansion, right? Volume coefficient of thermal expansion. Then I have thermal conductivity, then thermal stress. That's all the equations. Energy required to raise the temperature of 2 kilogram. So that is mass is given of the following material, okay, from 20 degrees Celsius to 100 degrees Celsius. Okay, Fahrenheit also it's given. Aluminium, steel, soda, lime, glass, and high density polyethylene. So here mass is given, right? Then the temperature change is given, right? Delta T is given. So I told you the value is MC delta theta. M is there, delta theta is there. C it's given there in the table, right? Not table, table. So aluminium, steel, the CP values are given. Constant pressure, the thermal coefficient, right? So you need to put that value and you can calculate. So you just can try it. And here we have aluminium heat capacity is given 900 joule per kilogram per Kelvin. Mass is given 2 kilogram. Temperature difference from 20 degrees Celsius to 100 degrees Celsius, that's 80. So if you multiply these things, you will have 1.44 into 10⁵ joule, right? Similar way you can calculate for steel, soda lime, glass, and high density polyethylene. So the heat capacities are given in the table. You take it, put it in the formula ms delta theta. M is mass 2 kilogram given. Heat capacity you can take it from the table. Delta theta is change in the temperature, that is 80 degrees Celsius. When you multiply it, you will get the answer, right? 19.8. Question number 19.8. 0.1 meter rod of a metal elongates. So we don't know which metal is that, but some metal elongates 0.2 millimeter on heating. So initial length is 0.1 and now final length is 0.102, right? Because here is meter and here it's millimeter. Take care of the units. On heating from 20 degrees Celsius to 100 degrees Celsius, right? Determine the value of the linear coefficient of thermal expansion for this material, right? So equation you know, right? Delta L upon L equal to alpha into delta theta, right? So delta L is a change. So change it's given 0.2 millimeters. Delta L is given, right? 0.2 millimeter change. So I'll put in millimeter. Okay, delta L is given. L is given, that is 0.1 meter, right? So I can put it as 10 millimeter, right? No, 10 millimeter, 100 millimeter. Okay. Delta L upon L is equal to, so the question is alpha, right? Value of the linear coefficient. So alpha is question. Delta theta it's given 80. So from this you can calculate alpha. That would be 0.2 upon 80 into 100. So that will be coming as 2.500 and above minus 6. Okay.